Today we'll be going over an introduction to Power World. In today's introduction, we'll get set up with the Power World program and learn some of the basics of modeling, running a power flow, and fault analysis. By now, you should have already had Power World installed on your computer, the textbook edition at the following link. This allows you to model up to 40 buses, or more than 40 buses within the Power World software program. The typical demo product from Power World only allows you to model up to 13 buses, so this gives you a little bit more flexibility. Power World help files can be found on the Power World website. The latest version of the help files is for the Simulator 16 edition. Now it gives you a lot of very technical details on how to model things in Power World, how to troubleshoot if you have issues, where to find options, and set specific parameters of various types of modeling options. So today's lesson objectives include creating a new case, building your circuit, and configuring your options. We'll go through the Power World Simulator options, where you can find the power base, the MVA base for the system, navigate some of your case options, and investigate or explore some of the different units that you can represent within the Power World software program. Then we'll go into simulating your circuit. We'll discuss the difference between the edit versus run mode, running power flows, and running fault analysis. So to create a new case, you simply click on the file, open Power World, click on the File tab, create a new case. This will bring you to a case dialog or display screen where it'll allow you to build your own network. So you can go to the Network button on the ribbon under the Draw option, the Network button on the ribbon, and you can start adding buses, generators, loads, transmission lines, transformers, whatever you need to get your model started and running. As you build out your circuit, you have various options in configuring lines, buses, generators. You can add fields around different displays and create the circuit, move things around to your liking. So we will go to the actual Power World program, and I'll provide you a demo of everything that I've been talking about so far. So we'll start with a fresh case. We'll create a new case. In edit mode, click on Draw, Network. I'm going to start adding buses. I'm going to create a 3-bus system. I want my bus oriented upwards. I want my system voltage to be 230 kV. The shape and the size can be specified in any format you'd like. First bus I add is bus 1. I'm happy with just numbers for bus names at this point. And I build out my 3-bus system. I'll build just 3 230 kV buses. Just for experimentation's sake, I will change the orientation of bus number 3. Okay, now that I've added my network buses, I want to go in and add transmission lines. So I click once on bus 1, drag my cursor over to the bus that I want it to connect to, double click, and the line is being drawn. I can enter the impedance information on the line. Now you're required to enter at least a series reactance for a line. It has to have a non-zero value in order for it to be represented as a line. It can be a very small value, but a non-zero value. We'll go through later what all these other parameters or options mean, right? MVA limits. We should all know by now what the series resistance, series reactance, shunt charging, and shunt conductance means. We are going to model a line as a closed line, which means the device is in service. For the display, there's some options you can change there. For transformer controls, this is not a transformer, so that transformer tab is going to be left blank. We don't have any series capacitors on this line, so you don't have to worry about that in this instance. This will be of interest to us, how we choose to model the line in positive, negative, and zero sequence. So we have an option for zero sequence impedance, for zero sequence shunt admittance, and for ground impedance, if any is going to be represented. The owner area, zone, and sub won't be relevant to us for this application, but in a real-world system, you may want to represent different areas of your utility may want to represent different areas of their service territory, or a transmission organization may represent different regions by designated owners or areas. And then there's other custom parameters that you can enter as well. Okay, so a series reactance of 0.1 per unit is what we'll enter on a 230 kV voltage rating. Okay, I've got my first line modeled. Now I will model my second line. Click on that bus. I can click to create inflection points in the line and double click wherever I want that line to end. Here we see that line is represented from bus 1 to bus number 3. I'll enter 0.1 per unit series reactance again. Hit OK. I will now draw my third line from bus 2. That one didn't take, so I gotta go try that again. Transmission line, click on the bus once, create my inflection points there. Series reactance of 0.1 ohm again, or 0.1 per unit, sorry, it's not in ohms, it's in per unit. And there you go, I have a 3-bus system modeled. Now that the 3-bus system is modeled, I want to include a generator, perhaps a load. I will want a generator at this particular bus. I will designate 0 MVA, 0 megawatt output. My megavar output will be 0 as well. For the display, I want this generator pointed to the left. And back on my power and voltage control, if I were running power flow and I wanted the machine to respond to changes in the power flow or to respect limits, not allow the generator to exceed the megawatt setting thresholds, I would either check or uncheck these values. AVR means automatic voltage regulation, so it will, in the power, if I'm running a power flow, I can have the megavar output change to maintain bus voltages within a certain range that you would see here, which bus I'm regulating and what its set point voltage would be. Okay. For the generator, it will be of interest to us in running faults, what the neutral representation looks like. In here, neutral grounded is the default configuration. If I choose to model a generator step-up transformer, as part of this, I can just have an integrated model, so the step-up transformer will be part of the generator, or I could model it explicitly. And I can include the internal sequence impedances of the generator. So the R and X for positive, negative, and zero sequence. The neutral to ground impedance, if there is any. We'll model these for right now. We'll actually enter a 0.2 ohm positive sequence reactance, so 0.2 ohm, or 0.2 per unit. I keep saying ohm, but it's per unit. And everything in Power World here as we enter them is in per unit. And the generator MVA base here is represented as 100. If these values were given to you on a generator base, you could enter them in Power World. Just make sure you change that. It will convert everything to the system base. So on a 100 MVA base, which I happen to know is the default for Power World, but I'll show you where we can go check those assumptions. So my positive sequence impedance, 0.2 per unit, negative sequence impedance, 0.2 per unit, and my zero, I'll make 0.6 per unit. I'll leave the neutral to ground impedances as zero. Okay, there we go. So I've got my first generator model. If I wanted to change the size of it because it looks awkward relative to the rest of my circuit, I can change that to a 10 in the generator info display. Just move the megawatt, megavar output parameters out of the way. I'm going to add another generator on bus 2. This time I want it pointing to the right. I want it the same size as the other generator. For fault parameters, I'm going to enter smaller values than what I did at bus number 1, for the generator bus number 1. So 0.1, 0.1, and 0.3 per unit for positive, negative, and zero sequence impedances. Okay. I didn't specify a generator megawatt output, so even 0 as a megawatt output will be fine. Right now I've got no loads on the system, so 0 megawatt output is technically matching load plus generation at this point. For a power flow to run, what we'd need to do is to designate a slack bus, but more on that later. Okay. So as you can see, we've created our own complete circuit model. We've got 2 generators, 3 buses, and your system should be represented something like what's shown on the drawing here. As we go to the different simulator options, we've got in Power World, on the ribbon, an Options tab. The first item on the Options tab is going to be Simulator Options. So before we go into the running the power flow information, we'll look at those simulator options. So simulator options will include your power flow iteration convergence tolerances and maximum number of iterations, your megawatt control type application, so whether I want to do automatic generation control, whether I want generators responding to changes in the system, like if I take a line out or if I lose one particular generator, do I want one slack bus generator to respond, or do I want all generators on AGC to respond? I've got other control loop other control loop options that I can check, generator VAR limits, voltage control type applications. Under advanced options, here's where I'd have the ability to go define power flow solution details and what I want for economic dispatch and other types of results that I'm looking for. Again, voltage and tap changing on transformers and how I treat that. We'll skip over the island-based AGC, move on to just the DC options here, whether I want to run a DC power flow, how we treat DC power flow, so ignore line series reactance or resistance, just assume a reactive lossless line. This is not an uncommon practice for certain types of analysis. As I come to my general options, I have the assumed MVA per unit base for the entire system. I can change that system base from here. That's probably the more important option that you'll want to verify in your own Power World setup that is consistent, whether you're putting everything on a 100 MVA base or 1,000 MVA base. Because as I said earlier, when I was erroneously saying line reactances were being entered in ohms, right? Everything in Power World is entered on per unit values. So that's all we're interested in today for Power World simulator options. We'll exit from there and see what our next task is on the slide deck. So now I'm interested in running a power flow or running a simulation on the circuit. So we've built a circuit. We've entered all our impedance parameters for generators and for our transmission lines. We've designated a slack bus. We don't have any loads in the circuit that we built, which is fine for our example. I want to highlight the differences here between edit mode and run mode. So in run mode, it will not allow you to run a simulation or perform any simulation. In edit mode, it won't allow you to perform any simulated or any of the simulations. So you have to go to run mode to have simulations performed. All right, so we'll show you an example of that. So we were at the draw tab. We're on the draw tab looking at that ribbon. Okay, everything with our system looks fine. We want to go to tools, and that's where our solve button would be. So we can do a single solution, but we want Power World to run to do its thing with its graphic user interface showing us how a power flow would solve. So as soon as I hit run mode, you see the options become available for me. So going from edit mode to run mode, I will only have edit mode, all these options are grayed out. In run mode, I will actually have the options to perform my simulations. Okay. Okay. So continuing on. We've identified the differences or the issues with edit mode versus run mode for me to run any simulations, be it fault analysis or my power flow. I need to be in run mode. For me to run a power flow successfully, I have to have designated a slack bus. I want to set my generator outputs, and then in run mode, I'll hit solve. Now, you'll notice that I have not yet designated a slack bus because I do want to show you one thing. If we come to fault analysis and then go to options, I can use a solve power flow, and there's these other options out here. The flat IEC 909, flat classical, or use existing voltages. As I just want to run a single fault, I'm going to hit run fault. It tells me there's no faults to solve. Okay, so I need to use this dialog over here. I am going to attempt to do a bus fault, single line 3-ground fault at bus number 1. Calculate. It'll tell me the fault bus is out of service. Okay, if I go back to my power flow 1 line, I can see, well, everything looks fine. Everything's energized, right? My breakers show that they're closed. Why did I get that error? It's because I didn't run an active power flow. You can handle that by coming to my options, flat classical, go back to running a single fault. Options. My flat IEC 909. It will give me fault parameters starting at 1 per unit voltage. I can try that one. Fault bus is out of service. Okay. So then I'll try using existing voltages. Running a single fault won't allow me to do any of them. So I've got to come back here. I've got to come back here and actually run my or designate one of the buses as my system slack bus in edit mode. Designate this as a system slack bus. Okay. Now that I've done that, go back to run mode. Another way to access the fault analysis display, right click on the bus, hit fault. I want to run a single fault at bus 1, single line to ground. Now when I hit calculate, I actually get my fault current results. So for a single line to ground fault at bus 1, A phase is always the odd phase out. So if it's a single line to ground fault, A phase will be the faulted phase. If I do a line to line fault, which I'll do here just to show the example, A phase is the odd man out, so it's the unfaulted phase, and B and C are the faulted phases. Okay. I can see here that I've got now bus records, line records, generators, loads if I had any, switch shunt buses, and I can actually get my Y bus matrices from the power wheel display. Positive sequence, negative sequence, and zero sequence networks. Okay. So I've shown you an example of all the common errors that you could run into in trying to run a short circuit, right? Going through the different options, trying to use the pre-fault volt profile. I couldn't do anything until I designated a system slack bus. Next question will be, well, how do I start from this? Or should I start from a solid power flow, from some other assumption? How do I set my pre-fault voltage to be a voltage higher than 1 per unit? And that example will discuss with what those options actually meant. So our pre-fault voltages, navigating to the options, selections include the 4 that we attempted, and there's another option to scale the result of the short circuit study. Okay. Because I've already been using the fault analysis module, it will be right here, so I maximize that screen. I come back to the options now. I can select, if I select start from a solid power flow, it will provide me power flow results on the solved circuit that the solved power flow that was executed. Now, notice that we did not solve a power flow to start with. We haven't done that yet. If you did solve a power flow and bus voltages range between typically plus or minus 5%, you could potentially get inconsistent short circuit current results. So the preferred options would be to run a flat IEC or a flat classical where voltages are fixed to usually 1 per unit. If you're using existing voltages, that would be if you open a case or you're sending case between engineers, you don't even want to start with the power flow. You just want to use the existing data set and run the short circuit studies from there. All right, so let's go look at an example of trying to evaluate the bus records. I'll go back to single line to ground fault, calculate fault current for fault at bus 1. Those are the results that I see. Here we see short circuit current magnitude is 6.7 per unit. If I wanted to see what that was in amps, it would provide me that value in amps. And bus 1 is a 230 kV bus, so you can do the math yourself. What the conversion from per unit to amps would be, you have it there. The next option I want to look at would be, well, if my pre-fault voltage was 5% higher, then if I scale the results by 5%, hit enter, fault current magnitude scaled. It gives me a value that's 5% higher. That would be if you're solving a circuit where you're assuming pre-fault voltage is 5% above nominal for all buses operating with voltage at 5% above nominal. Alternatively, I could have gone into my options, flat classical, assume that my profile options were 5% above nominal voltage, come back to my single fault, recalculate. I should get roughly the same thing. If I take away the scaling, then you see that the values are exactly the same. So you got a couple different options on how you can scale the fault current or assume a higher nominal voltage than just the default value operating at 1 per unit. Okay, now something else that you'll need in Power World will be in looking at my system here. I do want to go through some of the items that are frequently asked questions. So when I go to edit mode, I see these pi displays with the big circle with the amp reading on the line. But when I hit run mode, those values disappear. They go away. So if I look at my line information dialog, if you want those values to stay, you'll want to enter a rating of the line. As long as the line has a rating value entered, so the MVA limit, we will retain those pi display or pi diagrams when we go back to run mode. Okay, if I want to run a power flow, I can do it without including any loads, but let's make it fun, and we're going to put a load in at bus number 3. So we want maybe a 100 megawatt load operating at 100 megawatt, 150 megavar, so somewhere in the 90% power factor range. We do want it oriented down because of how we draw our system. Now, depending on how you draw your system or where you're adding the loads, your load orientation will be different. I've got a designated slack bus. I have my megawatt values for generators set to 0, but now I have a load. So on my first iteration of a power flow, I'm going to get a mismatch of a load and generation of 100 megawatts. So the iterations will create the profile that would be expected for this particular circuit, where the slack bus will try to serve all load, the 100 megawatts, plus losses, if any would occur, to energize these transmission lines and shift the power across the system. So now in run mode, I want to go to tools and I hit solve. There you go. You see the relative loading on each line, the pi displays. You see that each of the generators responded to provide reactive power. So 30 megavar being provided by generator 1, 28 megavar being provided by generator number 2. That adds up to more than 50. So the rest is supplying losses on each of the transmission lines, reactive losses on each of the transmission lines. Now, you should be asking yourself, well, I can't see any of the bus voltage or angle values or any line flows on any of the lines. How do we acquire or access that information? So I'll stop the power flow, and we will go to bus information dialog so that you see what the voltage at the bus is. So at our slack bus, I expect 1 per unit voltage at a 0 angle. At the load bus, I would expect some amount of voltage drop and an angle that is smaller than the slack bus angle, so negative 3.9 degrees. So that all looks like it makes sense. And at this bus, I would expect a smaller angle. Voltage here is at 1 per unit. So relatively simple. What if I wanted to see that information on the actual power flow display? From edit mode, for a bus, I would go to add new fields around the bus. I want to add bus voltage magnitude in per unit, and I'd like to add bus angle in degrees. So just for simplicity's sake, I'll move our gen out the way. I'll do the same thing on this side. I'm going to add new fields around the bus. I will add fields in position 7 per unit bus voltage and bus voltage angle. Okay? And I'll do the same thing at bus number 3. Add new fields around the bus. In position number 1, per unit voltage and bus voltage angle. Okay, there we go. And those are consistent with the values we had just seen looking at the individual buses from the bus information dialog. What if I wanted to see the power flow on each one of the lines? I can add new fields around the line or transformer at position number 3. I want to see megawatt flow. I want to see at position number 4 megawatt flow. I can also do any one of the others looking at amps or some other parameter. So there you go. I'm just going to move these out the way so I know exactly which line they're referencing. So 33.65 megawatts and 0.57 megabar. If I were to look at the other end of the line, at the 2 bus, megawatt flow and megavar flow. Again, because we modeled this system as a lossless system, we don't expect any change in a lossless, meaning no resistance in the line. I expect the same value for megawatts at either end of the line. Megavars can be different at either end of the line. So I'll run my active power flow. We can change the value of load and see how that affects my power flow. We can change that while it's running. Now I've got an overloaded facility. You can see the difference in bus voltage angles and per unit voltages. Okay, so I want to change this back to a more reasonable value. So back to 100 megawatts. Okay, there we go. Okay, some other information about how you can navigate or how you can verify information in your case. If I go to case information, look at Model Explorer, the Model Explorer option, I see here a long list of tables that are accessible to me. I can go to the network, branches, inputs. I can see each of my lines is opened or closed, whether it's a line or transformer, my RXB, and any of the limits that I choose to model. Just for an example, I'll double click and change that to an open. When I minimize this and I go back to my actual power flow, from the Model Explorer, I can manipulate my network. I just changed the status of each of the line from the Model Explorer. I can go back here, close it back in, look at branches state, whether they're open or closed, what the actual flow is on each end of the line, losses, real and reactive losses. So here we can see I have some megavar losses being incurred on a couple of those branches. I can look at my buses and see what the information with the nominal kV per unit voltage and the power flow voltage and angle in per unit or kV looks like, whether there's load or generation on that bus. I can look at what I've modeled for generators to see the status, generator megawatts, megavars, whether it's on AGC or AVR, what the max min limits are. I can do the same thing for my loads. Mismatches are for power flow mismatches. So we see here, they must be very small mismatches because they're all showing up as 0. So probably out to 5 or 6 significant figures. It's a relatively simple system. I can look down here at my solution details and see Y bus for the entire system. So this will calculate Y bus a little differently than we've done in class because it may or may not represent the generator impedance in the Y bus diagonal entries. I can look at my solutions or information around fault analysis and the tools and add-ons. Fault analysis tab. Look at inputs for branches, whether I've got 4 branches, 0 sequence impedance is represented. Now Power World likely just calculated some 0 sequence quantities for my transmission lines. If I didn't enter them, I can see if there's any shunt devices connected at any buses. I can look at my generators and see what values were entered for positive sequence reactance, negative sequence reactance, and 0 sequence reactance. For fault output, I can see any of the values in a solved power flow from this particular display as well. So this should equip you with a number of different options to navigate Power World. You should be able to create your own circuits, run power flows, and run short circuit simulations. You should be able to navigate the different assumptions in short circuit assumptions, looking at pre-fault voltages or running different types of faults. And you should be able to do hand calculations to verify that your short circuit values are identical, in essence, to the values that you get from Power World. One more example that I do want to go through is looking at single faults. I had a generator at bus 1. Bus 1 was connected, the generator at bus 1 was connected through a much higher short circuit current higher short circuit impedance. So if I run a fault at bus number 1, I see 7 per unit fault current at that particular bus. If I ran the same fault, a single anti-ground fault at bus number 2, which was connected through a smaller generator impedance, I would expect to see a higher short circuit current magnitude, and indeed I do. It goes from 7.09 to 8.724. Why did that happen? Just a quick refresh. The impedance of this generator, I assumed, was 0.2 and 0.6 in 0 sequence. The impedance of this generator, I assumed as 0.1 and 0.3 in 0 sequence. So I expect higher short circuit current closer to the lower impedance device. And sure enough, that presumption is confirmed. Okay, that concludes this intro to Power World. Thank you for listening, and good luck in your own attempts to model circuits in Power World. Thank you.